Okay, we're going to discuss topic 17D and 17E. So 17D is just looking at the temperature dependence of rate constants. So it introduces the Arrhenius equation, which I know you've seen in a few classes. So the Arrhenius equation comes from experiment. So it shows that the relationship has been found between the natural log of a rate constant and something called the activation energy. This is just the gas constant and temperature in Kelvin. And this is called the frequency factor. Sometimes it's also called, and we'll see why in a little while, the steric factor. So you'll see A given both of those names. So if you look at self-test 17D.1 on page 742, you can see that if you measure rate constants at different temperatures, and then if you graph if you graph 1 over t versus, or if you graph natural log of rate constant versus 1 over t, you'll have a straight line, and the slope should be negative activation energy over r, and the intercept should be the natural log of this frequency factor. So when I did that on Excel, I got an activation energy of 23 kilojoules per mole. And then you take the intercept, raise e to that intercept, and I got a pre-exponential factor, or the frequency factor, to be 8 times 10 to the 10th in units of decimeters cubed per mole. So the EA and the A are called the Arrhenius parameters, and the EA is the minimum energy reactants must have in order to form products. You can just rearrange that, raise e to both sides so that you can also see the relationship is an exponential relationship with the activation energy. So the rate constant equals A times e to the minus e A over RT. And we'll see in a later chapter that this exponential factor really comes from Boltzmann's distribution. So we want to think, if we want to change the rate constant of a reaction, a catalyst changes the EA. So your book has many pictures where you essentially can say that if you have a reaction and if it has an activation energy, if you add in a catalyst, you can, if it's the right catalyst, find a different route from reactants to products that will have a lower barrier, therefore a lower activation energy. So with the catalyst, it's going to be smaller. So I'll call it EA prime. The other way to change the rate of reaction is to change the temperature. But from looking at this, when you change the temperature, you don't change the activation energy. You just change T in this equation, which impacts the rate constant. The reason it does that is essentially if you increase the temperature, so if we're at T colder and go up in temperature, you're going to have more molecules that have enough energy to get over that barrier in their collision. So temperature impacts the rate constant by changing the energy of the reactants. A catalyst changes it by actually changing the activation energy. So we're going to move on to talking about mechanisms. And oftentimes, the Arrhenius equation can give you information about a mechanism by giving you that activation energy, as well as the pre-exponential factor, frequency factor. So elementary reactions make up a mechanism, and each has a molecularity. So the molecularity is essentially the order of an individual step in a mechanism, whereas the reaction order is determined experimentally. The molecularity is determined because you propose a theoretical mechanism and you can look at the reactions. So if we look at it, for example, in this case, this first reaction of A to I is a first order has a molecularity of 1 because it's unimolecular, because this is actually a mechanism. This is not just the overall reaction. So this particular reaction we're going to start with when we think about a mechanism is something you could think of maybe for a radioactive decay. Oftentimes A might decay to one thing and then go on before, and oftentimes many, many more steps to form a more stable product. So if we look at this particular reaction, you can write how everything changes. So A changes in the first step in a negative way. I changes both by being made from A and going on to make P, the product. So you have two terms. And product changes just when that intermediate reacts. So we can look at the first step and we can integrate how A changes with time. So this is just a first order step. So this is the integrated rate law for a first order step. So if we want to see how the intermediate changes with time, we have two components to the equation. One of them, though, is really just how the decay of A. So you can replace the concentration of A from an integrated rate law for that first order reaction with how it relates to the concentration you start with, the rate constant for the first step, and time. So I've just replaced this term right here with the integrated rate law. So we can go on then. Now everything on the right-hand side is a constant or time, so we can integrate that over time. And on the left-hand side, we have the dependence on the intermediate concentration. And so if we start out with 0 intermediate, and if A does not equal B, then we can integrate that equation, and it's a common form. One of your problems is going to ask to prove that this integration is correct. So one of your problems in your homework will ask you to just do this integration that I just showed you. Sorry. So to actually carry out this integration, they say it's a common, or it's a well-studied differential equation. So you can go on to look at that, and you can see, let's see, that if you only started out with A, then the sum of A, I, and P has to equal A0. And you can substitute that in for I, and you can get an expression for the concentration of P as a function of time, because A0 replaces A with the exponential factor. So you can go from knowing the concentration of I as a function of time, the intermediate, to the product as a function of time. And if we look at what that graph looks like, depending on the rate constants, you tend to have the reactant in pink just going down in concentration, the product increasing, and this intermediate I comes in and then decreases as its concentration is depleted as it goes on to I. So when you look at that, you will see that there is a maximum. So there's a maximum concentration of I. So if you were concerned maybe about the potential radioactive nature of that intermediate or something and wanted to make sure its concentration had depleted to some concentration, you can look at that and self-test 17E.1 on page 748 will ask you to take a derivative of this and find out when that concentration is a maximum. So you should stop and try that problem. So the next kind of reaction we're going to look at is one that has a reactive intermediate, and we're going to talk about the steady state approximation. So this is a situation where you have a reactive intermediate, therefore the reactant's concentration is always pretty, or the intermediate's concentration is always pretty low. Therefore, the change in the intermediate's concentration with time, you can approximate to be about 0. Because if the concentration itself is super low, how it changes with time is going to be super low. So that's often the case if you have a free radical or some extremely reactive intermediate species. So yeah, so self-test 17E.2 on page 749 asks us to look at this mechanism for ozone in equilibrium with O2. And it tells you that the mechanism isn't complete, it's just part of it. But that means that if I add these up, I won't necessarily be able to see what the overall reaction is. So I can still write the change in ozone with time. So it's going to be depleted in the first step, created in the second step and depleted in the third. So you have a negative, positive, negative. So notice I'm taking the molecularity of each step, and I can directly write a rate from that. So because this is actually telling me for this step to take place, an O2 molecule has to hit a free radical, an oxygen atom. So it's actually telling you on an individual atom or molecule basis what's happening. So we can take each of those and write the rate. You can't do that with the overall reaction. So when we look at how the intermediate changes with time, so it's created in the first step, used up in the second, and used up in the third, so plus, minus, minus. And we're going to use the steady state approximation. And when we do that, what we're going to say is that's approximately equal to 0. So that would mean if I want to, let's see, yeah, it's really this, I want to know the rate at which ozone is formed. So that means it can be a function of O3 and O2, but it can't be a function of an intermediate, which I never know the concentration of. So if I set this equal to 0, I can rearrange and solve for the O concentration. Then I can go back to my rate of change of product with time, and I can put in this expression for O every time I see it. So 2 places, I'll put in my expression for the concentration of the O radical. And then I'm going to look at that first term, and the second 2 terms have the same denominator. So I'll just multiply the first term by the denominator on top and bottom so that I can group the terms. When I do that in the numerator, you can check my math. So when I multiply this through, and I multiply each of these through in the numerator, I end up with this whole expression. And when I end up with that whole expression, I have a negative term and a positive term that are the same, so they can cancel. And I end up with, yeah, where did I? So at this point, this is a 1. So I end up with this term twice, and it has all the same things in it. So it's going to be -2 times this term. And then they're each to the ozone squared. And then I put back in the denominator, and I see that that is my rate law. So it's a rate law which has a complex order. It doesn't have a definite order with respect to anything. So if we want to think about this was a way to simplify a mechanism, simplify a rate law by looking at a mechanism and making approximations. So that was making the steady state approximation. You also remember making the rate determining step approximation. So that's based on the idea that if a step in a mechanism has a much larger activation barrier than the others, that essentially means that this step is super slow, but as soon as that happens, these 2 reactions take place quickly. So you can often take a mechanism and write a rate law just based on the rate determining step. So the other approximation we can do is called pre-equilibrium. And so this is self-test 17E.3, where you have a reaction where A is in equilibrium with I, and then I plus B goes on to form P. This first step we say has an equilibrium constant. We'll see how that's related to, we'll call them Ka and Ka prime. So if I write the rate of the reaction, it could be equal to how the product concentration changes with time. And so that would be equal to Kb, the second step in the mechanism, times the concentration of I times the concentration of B. But once again, if I is an intermediate, I don't want its concentration in my rate law. So I'm going to try to find a way to solve for I. When this first reaction happens fast, so Ka, Ka prime are super big compared to Kb, that means this first step can reach equilibrium essentially. So that means you're at the point where rate forward equals rate backwards. that's equilibrium. So if I rearrange this, I could put, I could take the concentrations over to this side and then take the rate constants to that side. So the ratio of the concentrations is equal to the ratio of the rate constants, and that's going to be equal to our equilibrium constant. So this shows you that an equilibrium constant is actually related to a ratio of rate constants. So you're thinking about relating equilibrium to the rate of a reaction. Once I've done this, I can solve for I, just like I did with the steady state, but I'm making a different approximation. I'll put that concentration back in here. When I do that, I find that the rate of the reaction is equal to some constants times A squared times B. So it appears like it's third, well, it is third order, but notice in the mechanism, there's no step that's trimolecular. Trimolecular reaction steps in mechanisms are very, very rare because it implies you have three things colliding. But that doesn't mean third order reactions are that rare, because a mechanism without a trimolecular step can end up to be third order. So, okay, so how can some reactions end up looking like they have negative activation energies? If we look at this, it's really going to be a matter of the relative activation energies for different steps. So if we look back at, is that the one I just did? Yeah. So this right here is technically KB, and then times K, which is KA over KA prime. So what you see for a rate constant for reaction in the lab is actually a ratio of rate constants for individual steps in a mechanism. So if you look at how the KR is impacted by the activation energies, you can write the Arrhenius equation for each rate constant. And then what you notice is the real activation energy, if we group all these terms, so this is going to be EA for the B step, EA for the A step, minus EA for the back step, A prime. And so technically, the activation energy, well, right here, is equal to a sum of all these activation energies for the individual steps. So depending on their relative values, you could end up with an apparent EA that's negative, which would mean the rate constant would decrease as temperature goes up, which is not something you think is normal, but it doesn't mean that you have a negative activation energy for any one step. It means that overall, the relative activation energies add up in such a way to make it appear that way. The last thing mentioned in this is this idea, if you have two possible products from a reaction, then you can write the rate of each of those. So rate of P1 over PT and the rate of P2 over DT. If you take a ratio of those rates, then if you're looking at the same time period, the DT goes away, and the ratio of the rates is really equal to the concentration of P in the two different reactions at any one time. So when you take that ratio, if I take 2 over 1, I get the ratio of the product from the second reaction divided by the concentration from the first reaction is equal to a ratio of the rate constant. So you can determine how much of your products will be formed at different times just based on which has the larger or smaller rate constant. So that would be a kinetic control of which product is formed. If you wait long enough, you'll get to the point where thermodynamics will take over and you'll get a ratio based on which has the larger delta G. But in the short run, as the reaction's taking place, the fastest reaction is going to give you the most product. So that's all I'm going to talk about from topic 17 or focus 17. You guys are going to present some examples of mechanisms in class for the last couple sections.